personally enjoyed reading his papers on Local SGD, some of the earliest papers on Local SGD, but this recent one which actually fills a very important gap in the theory. So without further ado, let's hear from Ahmed.
Thank you. Thank you for introducing me, and thanks everyone for being here. I'm really glad to be here. So today I'll be talking about this work on understanding outer optimizers. And I'm guessing, after this day of talks, we're a bit familiar with these. So this was work that was done in collaboration with people at Google DeepMind, as well as my PhD advisor. So Satya and Khaled, Arthur Duyard, Rob at the time was at Google as well, and Manzil is at Google, and Chi is my PhD advisor. And yeah, so this was published in Europe's 2025. So kind of the starting point is that training runs are now larger and even more distributed. So frontier models require tens of thousands of GPUs to train. This is no secret. It's extremely expensive. And building and maintaining some of these clusters is a very expensive thing. And cross-cluster training right now is not in vogue, but it might be. And this is not a theoretical problem. So this paper on DLCO, which we mentioned a lot, mentions this explicitly. There is a startup called Prime Intellect that is mainly trying to do this sort of very distributed training. And another startup that is also trying to do this very distributed training. So people are really interested in trying to make this work. OK, so, and one might ask, given all of these investments, is there room for improvement? And so some public data that we have is that even on training the DeepSeek v3 model, the model flop utilization is kind of just a measure of how efficient you are. And usually people aim for like 40% or 50% model flop utilization. This means that for 60% of the time, your accelerator is kind of not really doing much. So there is quite a lot of leeway there. For smaller models, this number can go all the way up to 90%. So certainly, yeah, there is some leeway there. OK, so, and yeah, this figure is from this paper, which was written by people at DeepSeek. OK, so kind of the main setup that we have is that I'll say we will have M devices. We are trying to solve this classical minimization problem. We assume that the optimization domain is unconstrained, and we assume that each device has access to stochastic gradients that are drawn from the same distribution. Now, this is quite different from the standard federated optimization setting, because we usually say the data is heterogeneous. But here, the heterogeneity is not coming from the data. The heterogeneity is coming from just like using many devices that are potentially far from each other, and communication is difficult. So yeah, it's a bit of a simpler setting theoretically to analyze than the full heterogeneous optimization setting that is kind of the standard for many of the papers in this field. OK, so I will give a short overview of data parallel training. Like this is the way that standard data parallelism, standard sort of parallelism is done. A very simplified look at it. And basically, the idea is that we replicate the model parameters and optimizer states on each device or each group of devices called a data parallelism group or a DP group. And each device does the following. First, we will fetch a local mini-batch. This will come from whatever chunk of the data set is on this device. And it is sampled like a IID. So all of these devices have data drawn from exactly the same distribution. We compute a gradient on this mini-batch. And all the devices will do this in parallel. They will compute gradients on different mini-batches. And then we will synchronize these gradients using something like an all-reduce. And then all of these devices will get the synchronized gradient, and then we'll apply the same optimizer step in parallel to update their model parameters. And crucially here, we basically have a one-to-one mapping between how often we communicate and how often we apply an optimizer step. there are many ways to improve this. For example, you don't actually need to replicate optimizer states at all. You can shard them at 0 additional cost. This was like the deep zero paper, deep speed, sorry, paper, the zero redundancy optimizer. And people will usually use many forms of parallelism in addition. However, all these forms of parallelism are kind of combinable with this approach. So the approach that we talk about today is an alternative to data parallelism. And if you use tensor parallelism on top, if you use any sort of of these tricks on top, they can still work. Okay, so kind of a more mathematical formulation of writing this is that each client will have the same model parameters xt. And then in parallel, we will fetch a mini batch from the data set, compute a local gradient, gmt. M here is the counter for the device or the client. And then we will average them, and then we will apply an optimizer step from xt with the gradient gt. If anything is unclear, please stop me and ask a question. If it's very expensive to communicate, as in a hypothetical cross-center training run, then instead of all reducing gradients, we may all reduce cumulative updates after several optimizer steps. Now that's a mouthful, but this basically results in this sort of algorithmic template, where they all start at the same model, exactly the same as before, but then we do several local updates. These are all optimizer steps, H of them. And then we will do some sort of aggregation. We will take the cumulative update and we will average that. And then we will apply another outer update. So this local optimizer, local update, what it does is that it will have an input model state, it will compute a gradient, and then it will do an optimizer step. So kind of we encapsulated some of the previous slide here, where now we are doing multiple of these local steps without synchronizing. So over time, these models will diverge from each other. And of course, parallel to this, we need to specify an outer update. And this outer update, it will take this average aggregated update. It will take this input, the global model state, XR, and then it will apply an outer optimizer step. So now I need to also keep track of where I started, XR, the point I started the communication round at. And very crucially, we here, this outer optimizer, gradient descent, and nest theorem of acceleration, anything like that, it accepts a gradient, okay? But we are not giving it a gradient. We're giving it something else. We pretend that this aggregated outer update is a gradient. But actually, for even a quadratic, you can write this down. Or for many kinds of functions, you can write this down. And you can show that in many cases, this cannot be a gradient. Gradients have to be conservative. This is not. So yeah, so this kind of begs the question of what are we doing here? One thing is that the communication improvement here is clear. If I can get the same result with the same flops as doing this, then I'm now communicating less by a factor of h. I'm only synchronizing for r times rather than r times h as I was doing previously. And kind of to make things concrete, local SGD is kind of the standard algorithm for federated learning for a long time. You have an inner optimizer, which is just stochastic gradient descent with a step size eta. And the outer optimizer, we can look at it as gradient descent with step size 1. So basically just, if you write down this update, xr plus 1 is equal to xr minus, this should be the learning rate here. We just set it to 1, and then we do this aggregation. You work out the math, and it's just averaging models. So local SGD can be seen as this sort of very simple model fusion, where I am just averaging all the models that I have reached at the end of the trajectory. DLCO is doing something different. The inner optimizer is Adam, or Adam W. And the outer optimizer is nest theorem of accelerated gradient descent. And this choice was motivated by superior empirical performance, as Duyard and So, this is kind of like, again, the same thing, but in a more mathematical way, which is just we're saying we broadcast this XR. We start with this Y sequence. This is the local models. These are the global models. And then we do H updates in parallel on each node. And then we communicate this last guy to the server. The server can communicate the update or the outer gradient, and then applies this outer update. I want to say that in practice, all of these nodes end up becoming like a server. Like we just replicate this computation. So yeah, the server model is not really in vogue here. And yeah, this is a two-level optimization structure, where now instead of using one optimizer, I'm using two. One for these local steps and one for this outer update. And apparently just averaging is not good enough. Like something else is better. So yeah, local SGD is effectively doing model merging through averaging. It's effectively using one optimizer, but DLCO is doing something more complicated. It requires to use two optimizers. And this two-level structure is a little strange. Honestly, it was very strange to me. It always struck me like putting a hat on a hat, like someone, I don't know, like that. Like, why are you applying an optimizer and then coming back and applying another one? So this was the main question of this paper. Why and when is this two-tier optimization structure useful? For simplicity of analysis, mostly to make this tractable, the inner optimizer in this paper is fixed to just gradient descent or stochastic gradient descent with step size eta. Well, we consider the following outer optimizers. We will consider gradient descent, but with an arbitrary step size, gradient descent with momentum, where the step size is gamma and the momentum parameter is mu, and nested of accelerated gradient descent. So this kind of brings us the closest to DLCO style methods, which to this day, as far as I know, we don't really have good theoretical analysis and understanding for. But this is the closest that I think we have. So for some technical assumptions, we will just assume that the loss function is differentiable and convex as a function of model parameters. Now, of course, real loss functions are not going to be convex as a function of model parameters, but this is also for tractability of analysis, really. You have to assume something. And we also assume that our function is L smooth, so the gradients don't vary too much, provided that the model parameters don't vary too much. And all the stochastic gradients are unbiased in expectation and have bounded variance. And then they are unbiased to the same function. So this is like what encodes the IID assumption that I am talking about. And in ordinary federated learning, we would have, like, rather than f, this would be fm. There would be a different function for each node. But here, I'm doing language model pre-training. I control the data set. I control what goes on these nodes. And I can just make them all have the same distribution. So the simplest form is inner and outer updates are both gradient descent. The inner update is this gradient descent with step size eta. The outer update is this gradient descent with step size gamma. And for this algorithm, people have called it generalized local SGD in the literature before. And for this algorithm, we have many papers that have previously studied it. So this paper is Scaffold by Karim Meredi and co-authors, some of which are here. FedEx, again, like by people from CMU, some of which are here. And yeah, on this like server-side step sizes and sampling without replacement by people from KAUST. And yeah, these are all very useful papers. A difficult limitation is that when we study this problem in the heterogeneous setting, there is very little that we can say. Essentially, we are forced to be extremely pessimistic. And one difficult limitation of that is that we are forced to use these very small inner step sizes. So our work studies a simpler setting, an IID setting, where we can potentially say more. And by the way, the difficulty in the heterogeneous setting is kind of tight. Like in the worst case, you just suffer there. So this seems to be a setting where we can actually say something a little bit more and understand this trade-off between inner and outer step size in a more clear way. And I want to say that for the other algorithms we study, momentum has been previously considered in the literature, but as far as I know, none considered Nesterov style acceleration in the outer optimizer. So this is, this is uncharted territory. Okay, so this is our main theorem. We consider generalized local SGD. The inner step size is eta, the outer step size is gamma. We run for R communication rounds with H local steps. And we basically get this kind of familiar structure where we have this term, which can be called the optimization term. This is the term that basically says, if I had zero noise, how far would I be in minimizing this function? And this is a variance term, and this is a drift term. So this drift term with H tells you how much these clients, like the effect of the clients drifting apart during the local optimizer process. And even for IID data, the model parameters will like drift apart during optimization because it's like a random walk. And this variance term, very crucially, it has eta and gamma, but their effect is different. So there is some asymmetry there, and we see the same asymmetry in the condition on the step size. So the condition to get this convergence rate is that like inner step size multiplied by smoothness constant, and we have this gamma minus 1 plus h is smaller than a constant. And this plus is just like the maximum of whatever is inside and 0. So if gamma is equal to 1 or is smaller than 1, this term vanishes, and I only get a requirement that eta is small enough. However, if gamma is much larger than 1, then now I need to start forcing my step size eta to be very small, or like smaller than 1 over h, the number of local steps that I take. So this asymmetry here between how the two step sizes show up both in the bound and both in the step size condition is pretty new, and it kind of is the key to explaining this dichotomy here. So essentially what this shows is that the outer learning rate helps handle a trade-off between optimization speed and stochastic gradient noise. In the sense that if I fix the outer step size to 1 and I try to make the inner learning rate very small to kill the drift term or the variance term, then I am forced to basically suffer slow conversions. So if the noise of running local updates is larger than the gains in the optimization term, like you drift too far, you want to make your inner learning rate small, but you have no mechanism of making up for that if you fix your outer learning rate to just be 1. So when the variance and drift terms are naturally small, or when the inner learning rate is very small, setting gamma larger than 1 could accelerate optimization by reducing this first term, and these other terms are already small enough. So essentially, manipulating those two allows the algorithm kind of at the extremes to smoothly interpolate between vanilla local SGD, this is a well-studied algorithm, and mini batch SGD, which is also a well-studied algorithm. If you fix gamma is equal to 1, this step size just becomes eta L smaller than 1. This allows for a large step size independent of the horizon. And this is kind of as good as it gets for local SGD. And for mini batch SGD, if I decide to shrink eta very much, we can think of mini batch SGD as eta is equal to 0. I just don't move at all in the inner optimizer step. Or eta like some epsilon. And I set gamma to make up for that. We can get this regime. So these are the two extremes, but we can actually explicitly solve for the optimal pair of inner and outer step sizes for whatever noise regime that we are in. The solution suggests that in the worst case, using an outer learning rate that is smaller than 1 is just not very useful from an optimization perspective. We will either set it to 1 or larger than 1. Now, this doesn't exclude that such step sizes can be useful from a generalization perspective. So for example, in the look ahead paper, there's something similar to this, and they show some generalization benefit to an outer step size smaller than 1. So kind of the main takeaway from this theorem like beneath the math, is the outer learning rate can fix an inner learning rate that is too small, but it cannot really save you if the inner learning rate is too large. And intuitively, it makes sense. If the inner learning rate is too large, your nodes diverge. Whatever synchronization you do doesn't help. And a counterintuitive conclusion here, which is kind of surprising, is that we shouldn't be afraid of trying outer learning rates greater than 1. And this is very surprising, because usually learning rates are on the order of like 10 to the negative 3. And now I'm saying like make them like 2 or 3. So kind of like momentum is kind of the same story, but for every gamma that you see in the previous theorem, we replace it with this effective gamma, which is gamma over 1 minus mu, where mu is the momentum parameter. But the takeaways are the same. It's just like what you are, like the mu parameter ends up shaping like the step size condition and the step size condition and the bound. But it doesn't really affect the story. It just affects, like the scale of the parameters with momentum. However, for acceleration, we can actually show like a much stronger benefit, which is you do actually get a much faster optimization term when you use acceleration. You get acceleration in the number of communication rounds, and kind of you get a similar story when it comes to the trade-offs of learning rates, but faster. It's like it's a free lunch. It's a win. And this result is like also interesting because there is prior work that is studying acceleration for local SGD, and using local acceleration, they kind of saw a similar rate as derived here. But turns out you can get the same thing by just using acceleration in the outer optimizer. You don't need it in the inner optimizer. So kind of to talk a little bit about empirical performance. We test kind of this prediction on pre-training decoder-only transformers on the C4 dataset. We did like 150 million, 400, and 1B. Scales are not very large, but they are trained to chinchilla optimality. So we kind of are doing that. The number of local steps, we varied between 50 and 500. The outer optimizers we considered is just like local SGD, Nesterov style outer optimizer. And we also consider schedule-free SGD. This is just to avoid having to specify a schedule. Just data parallel baseline. And we extensively tuned all of these. So we kind of ran pretty big grid search, I think. This burned a lot of money. So yeah, but so this here is kind of showing kind of what we already know, that Nesterov is performing a lot better than just simple averaging. You can see it's quite a significant difference in perplexity. And this difference, persists into larger scales. And and one thing here is that the best performing outer optimizer at the larger scale at 1B was schedule-free SGD. And very interestingly, the outer learning rate that we set there was 2. So it was quite large. You can see the difference with an inner learning rate is like 10 to the negative 4. And kind of the story here is that I'm saying if you have to tune those two learning rates, it is better to err on the side of making the inner learning rate too small than too large. And the main takeaway here is that outer optimizers are actually useful. And maybe when we were tuning this learning rate, we should do it over a much larger range than for the inner learning rate. We have kind of reached the end of the talk. Does anyone have any questions? Yeah. Thank you.
I think schedule-free can be shown to also be sort of averaging. So it's hat, hat, hat.
Yeah, that's true. Yeah. I don't have a good analysis of schedule-free as an outer optimizer. But yeah, it is I agree. It is. We're adding one layer on top but that layer is designed to do away with scheduling, right? But now you have to kind of deal with that again. There are actually some deeper connections between schedule-free and DLOCO. So there is this paper by Courtney Paquette and co-authors. They have this algorithm called Dana or something like that. And yeah, they do study a lot like this deeper connection. And there's also a paper by Aaron DeFazio who was also interested. There is a deeper connection there between DLOCO and schedule-free. And I think we don't really understand it very well right now, but yeah. Yep.
Can I think of the outer loop, like if you take enough steps in the outer loop on the local devices, can I think of those as like proximal steps on your?
Well, no, because they can go too far. So if you limit the number of inner steps, yes, but if the number of steps is like enough, you can just minimize the function and not have to do any communication at all, right?
The
like,
local function, sure.
Yeah, in the local one, yeah. So it is. So if you use the proximal version instead, you get very different analysis, and I think it also just empirically performs a little worse. But I'm not sure if that is just because people are not tuning enough the regularization parameter in the prox or not. But yeah, it is not. It at least wouldn't give you the nice optimality condition that comes from a proximal step where you have like some nice closed form. I would say that the final iterate returned by these local optimization procedures after you do averaging can be very weird. It can be like, yeah, it doesn't have to really satisfy any nice condition like the prox.
Is there some theoretical reason in your results not to take infinitely many local steps?
Not to take infinitely many local steps?
Yeah, so that everybody would find a solution?
Yeah. So if your budget is fixed, then taking infinitely many local steps is not optimal. So let's say you fix a budget, a total number. What? Fix a computation budget and assign different. Like let's say you assign a cost C1 to communication and C2 to computation. Then the optimal pair of those will very much depend on these costs, and will also depend on this variance.
What if you said
communication, then it would be infinite?
If my only cost was communication, then yeah, in this setting, definitely I would just take infinite steps because you don't communicate at all, and they will just minimize all the same function. Yeah.
Oh wait, sorry. This is assuming that each local device.
This is IID. Yeah.
Has IID observations.
Yeah.
I see.
So in the heterogeneous setting, kind of a lot of this story collapses and doesn't work anymore, and you get a very pessimistic kind of view as to how useful local optimization steps can be, which doesn't really line up with what we see empirically. And a part of that is just when we're pre-training transformers, we actually do force the data set distribution to be the same. A lot of the time, the data, you're reading the same data set, like FineWeb or here it was C4 or something. Yeah.
It seems like optimal step sizes, like at gamma depends on L, depends on sigma, and you can derive the optimal step size to have a hierarchy, right? But during training, like sigma can change, right?
Yeah.
And maybe tuning both of the pairs eta and gamma are like.
I agree. It is difficult. So actually, funnily enough, this project started out as we want to do adaptive step sizes for DLOCO. Like this started out as we wanted to do something like that. But quickly we figured out we don't even understand without adaptive step sizes. I think we're a little bit closer, but I don't think we still have a good adaptive step sizer for DLOCO. The inner, in DLOCO, the inner optimizer is Adam, which is kind of adaptive, but the outer optimizer is usually something like Nesterov, and this bothers me. But
and for inner optimizer, you have Adam W. Do you have any schedule for that?
Yeah. This was using a cosine schedule. So you fix the total number of training steps, and you use a cosine schedule. Yeah.
Do you think there's way to? Because they communicate, maybe changing the schedule inside of the inner like optimization is.
According to this theory, definitely you should be changing them, but we didn't do that. Yeah.
One more question.
Yeah.
So you mentioned the acceleration. I think the previous paper which does this is this FedOpt paper by Tengu, but they
Yeah.
were not able to accelerate R, but they were able to accelerate H. I think.
No, it was the opposite.
It was the same as here?
No. Yeah, they were able to accelerate R and not H.
Oh, okay, then this is surprising somehow because here you add the outer optimizer
Yeah.
to be Nestor, but you still only accelerate
R.
I see. Do
Yeah.
you think it's possible to do accelerated inner outer and somehow extend your analysis in the homogeneous setting, or?
I think so, yeah. I think it should be possible. It would be messy. This analysis is already messy, but I think if you add acceleration on top, it gets messy, like inner acceleration on top. But I would suggest that it would make some of these terms better. At least here, I would expect that I could get an h squared instead of an h.
Right. So here you're not interpolating, of course, between the accelerated mini batch and accelerated local. You're doing something weirder.
Yeah, because here it's, like once you start adding acceleration in the outer optimizer, this interpolation doesn't really work. So here, I would say the benefit here is much more about conversion speed, but yeah. But there are still trade-offs between inner and outer, just not as clear as the story of like the previous theorem. Okay.
Let's thank Ahmed again.
Right. Thank you.
Now we have a half an hour break, and
I think we have one more.
we have one more.
Yes. Oh, is
It's
it
okay
break
if you
yet?
want to have a break.